Oh boy, such a simple topic caused such a big commotion. In my previous video I tried to give a simple, yet pretty effective and short solution to replace the crappy timing with delay. And the most important, it was aimed at beginners, because the unsigned integer overflow magic is confusing and takes some time to explain. Some of you guys asked for more details, so here you go. Still, some not-so-gentlemen failed to read the whole original article and tried to point out errors already mentioned in the article, and the best is, cry rivers for providing a buggy example and then gave a supposedly perfect solution, which is buggy. So buckle up, because we are taking a deep dive in the world of timing with unsigned integers. These slides are from my online embedded development course. We started at replacing the delay, because delay adds wait time and is not a proper timing mechanism for tasks. One easy and fast solution is using Arduino's built-in millis function to get the elapsed time. Note, the 32-bit unsigned timer overflows relatively fast, so it's not really suitable for real-life projects. There are much better solutions in industrial systems, but those require a much deeper understanding of embedded stuff, so keep it in mind. Arduino users are usually not professionals. So use millis to ask the current time, have some variables to store when to run and the period, that's it. But since we are talking about hobby users, they can and will make some mistakes, even pros do, just less often. Like schedule a long-running task with too small period. This solution, as I mentioned, is not a replacement for an RTOS, just a primitive yet effective way to schedule stuff. If many tasks have to run at the same time, of course we will miss some deadlines. This solution only removes the extra time spent on waiting. It's known that you can't schedule stuff after the 32-bit counter reached its max value. That's a harsh limitation, but really easy to understand for everyone. One of the provided solutions from Mr. Smart Guy was to store the last run's timestamp and subtract the period from the current time and compare this value to our last run. In theory, is the perfect solution, but it has two major problems. One, it's much harder to understand at first sight, and non-professionals need easy to understand examples first. Second, it's not bulletproof. Much better than the top, but I will give an example later how does it fail in some cases. But before that, it's bonus track time. Let's understand the basic problem. Why is this an issue? Only the Mayans ran out of calendar space in 2012. We can always print a new calendar for the new year. We will literally never run out of options to schedule future events. Our timeline is infinite long. We can literally talk about any point in time with arbitrary precision, because we don't have any limitation in languages. However, computers need to store data in an efficient way. Some computer engineers saved a few bytes by using 2-digit year representation in early computer systems, and it did count because the resources were really limited. It also resulted in the Y2K problem in the year 2000. The guys inventing the Epoch time were just a bit more thoughtful. Each Epoch timestamp is a 32-bit signed integer, counting the seconds since 1970. Every professional should use this, because it eliminated a lot of problems, especially those pesky time zones. But it only delayed the inevitable. The inventors will be probably long dead by 2038, but that's when it will reach its upper limit. You can't represent any time after it reached the end of the digital calendar. Of course, this will be resolved, probably by switching to 64-bit representation. It will delay the inevitable another 586 billion years. That's probably enough time to figure out something. So, if you reach the limit, calculations result in something unexpected, both signed and unsigned. It's practically a real-life Groundhog Day, because we have a loop instead of a continuous and infinite long timeline. So, to give a better visual representation of our millis and scheduled tasks, let's have both the delimited timeline and the circle. Our first example shows when a task is scheduled for future run. Should we run our task? Of course not. It's clear that the task is at a later point. And now, the current time is bigger than the scheduled task. Easy, the task should run in this case. Now let's wait a few weeks. We are getting near to the overflow event. Millis is greater than task, so it should run, right? Of course it has. And this is where the fun begins. Just look at the right task clock. What would you say is millis at a later point? I would say yes, but math says otherwise. At least for the straightforward solution. After the current time overflows, it will be always smaller than the scheduled timestamp. Our code practically stops working, and that's bad. The other subtracting method also looks a bit weird first. A negative number is usually less than any positive number, but not with unsigned integers. The overflow works the other way around too, and unsigned means it doesn't understand the concept of negative numbers. This is how -9 becomes a huge positive number, and now scheduling works. But does it work all the time? If we can keep all tasks under a millisecond, the straightforward solution will also keep working. But that's usually not the case. No one measures or calculates worst-case runtime during tinkering, so we can end up with a relative long-running task. If we keep doing calculation and miss a run while the current time overflows, the so-called bulletproof and perfect solution also stops working. If you still don't believe or you want to see an example, I wrote some test code to prove. So I prepared this sample code to show some cases when it works good and when it fails. We have our task, our last run for the two different implementations, we have our period and the current time. To be sure, we print to the serial terminal that true value will be some value and false value will be some value, so we can check if it's really true or false. So our first example is when the period is added to the task variable, the original implementation. So when our task is at 1, period is also 1, current time is 0, you can guess the task is scheduled for later run. So in this case, it should be false. Also we have task at 0, period is 1, that's not really interesting yet, but current time is 0. They are the same. Task should probably run at this case. And in this case we have task at 0 and current time is at 1, meaning we are very late. In this case we should run twice because we just missed one run, but that's not the point here. And then we have our int max value. That's the hexadecimal representation for all ones. I prefer to write like this. So it's before overflow. The period is 1. Current time overflowed. So our task is pretty late and in theory it should run. We will check if we can run it or not. And then we have plan B when we have the last run, the period and the current time. So when current time is 0 and last run is 0, then we should run only when current time reaches 1. So in this case, case 4, we shouldn't run, it should return false. Last run is 0, current time is 1. This is the normal case, we reached our time, this is time to run our task. We also have some late task. We have a normal case when the last run did not overflow yet. Current time did overflow. Of course, this is when our normal implementation fails, but this should say case 7 that yes, we shall run. And let's have another case when we didn't overflow with our runtime. Period is a bit longer because we have to wait longer, and current time did overflow. Should we run in this case? Of course not, but not time to run yet, it's in the name. And spoiler alert, this is buggy. We did not overflow with the last run, period is 1, and surprise, we had some stuff to do, too much time elapsed. We should run twice, but this is the case when we should run, but yeah. Let's try run this. True means 1, false means 0. Case 0, task scheduled for later run. Case 0, we don't run. Case 1, we reached the time to run. Yes, we shall run. Case 2, task is already late. That's not a problem. It shows that we shall run. And case 3 says task is late and overflowed, but this is where our code fails. After about 2 months, the result is wrong. we overflowed, and this is where the simple implementation starts to fail. If you have a simple project just for a weekend or something like that, it's not a concern for you. If you are making something more reliable that runs for weeks, months or years, then of course this is a concern for you. Now we switch to the bulletproof edition, and in the first case we shall not run task scheduled for later run, and yeah, the first bug, we are at current time 0, last run 0, period 1, and yeah, it already fails. It's already a bit buggy, but yeah, let's say everything has to run first. The second case, or case 5 here, task just reached scheduled time. Of course, when we reach the time to run, it shall run. The 1 is, or true is okay here. Case 6, the task is already late, so we missed one deadline already, so we shall run it twice, but at least it detects that we have to run. Case 7, time to run with overflow. This is where the solution is better than the original simple solution, because it starts to run correctly. Case 8 says that we are at really big last run time, period is a bit longer, we overflowed, it still runs correctly, but when we miss a single deadline, then the current time minus the period will also give the wrong solution. So this is where this solution is wrong. If we can't ensure that everything runs under 1 millisecond, we can also miss some deadlines, and then this solution also stops working. So this is not the solution for this. So how to solve this problem? Either create your own 64-bit timer to make it future-proof for the following few hundred million years. It would be the best if Arduino would include a 64-bit timer, but I'm not a decision maker. Or you could add some extra check to ensure proper operation in every single case. I would say go with this. Last but not least, using an RTC with some proper driver could give a solution for some other issues too, like power cycling. But that depends on an external hardware. I hope you learned something, and see you in the next video.